Now let's have a look together at L'Hopital's rule.
We talk about the limit of a function when, as the x value tends to a certain value, we say what is the y ordinate tending to, or what is the function tending towards. We can find out the limit of a function in different ways, including using the Maclaurin series. But now we're going to look at a different way to find a limit, and how when we find we're in the indeterminate form, we use L'Hopital's rule. Start us off with just with a visual here. This is a visual that you might have printed on a t-shirt or something like that. And by the time we finish this video, hopefully it will make a bit more sense to us. Okay, when we talk about limits, you should have come across them before. Certainly in year 1 of the Further Pure course, you should have come across rational functions. Let's have a look at an example to remind us. So we've got it as a ratio, a rational function of one function in x over another function in x. Here's our graph of the function, and when we're sketching such functions, the asymptotes are important to us. And of course, there's no value of y when x is 0, that's the denominator. But what we're interested in at the moment is what happens to our y values when x tends towards a very large number, tends towards infinity, or when x gets smaller and smaller, tends towards negative infinity. Another way of saying that is by using this notation. It just says, what's the limit of the function as x tends towards infinity? And a way to answer this question is by splitting our fraction up into 2 separate fractions. And once you've done that, we've got x over x, we know what that becomes, and then we've got 2 over x as well. And we can look at that and say, right, as x gets bigger and bigger, 2 over x is going to get smaller and smaller. It's going to tend towards 0. We'll never quite reach 0, but it will tend towards it. And so the limit that the function is tending towards as x tends to infinity is going to be 1 plus that 0, so just 1. Let's have a look at another example here. So we've got the graph, we've got the function. This time we've got a quadratic in the numerator and the denominator. Not so easy to split into separate fractions. What can we do with this? Well, what we can do here is we can divide each term in the numerator and denominator through by the highest power of x. What this means is any terms in that highest power, so here we've got our 2x squared and our 5x squared, that'll go to the 2 and the 5, but everything else is a fraction with x in the denominator, which means as x gets bigger and bigger, they will tend towards 0. Of course, that leaves us with 2/5. Let's look at one more. This time we've got x tending towards 0. There's a graph of the function. We've got some trig functions here now. So it's not tending towards infinity, it's tending towards a certain value. So we can substitute that value into our function. Once we've done that, we can work the values out. Now, cos of 0 is 1, sine of 0 is 0. So we're just left with minus 5 over 4. And if we look at our function, you can see minus 5 over 4, minus 1 1/4, yes. When x is 0, that is our value of our function. So, what about the indeterminate form? What's that? And how does L'Hopital's rule help? Well, let's have a look at this example. X is tending towards a certain value, it's not infinity, so we can substitute it into our function. But hopefully straight away, you'll notice we're going to have 0 as our denominator. So we're in trouble. We can't divide by 0, can we? Then if we look a bit more closely, finding sine of 0 as well. It doesn't help either. So when we've got 0 over 0 as our limit, then that's what we call the indeterminate form. Or also when both numerator and denominator are plus or minus infinity. So we can't find the limit using our methods that we've looked at so far. So this is where L'Hopital's rule comes in. His rule states that the limit of a function divided by another function as x tends to a certain limit is the same as the ratio of the derivatives of those functions as x tends to the same value. What happens if we've got those derivatives and we've still got an indeterminate value? Well, L'Hopital also tells us that we can go on and use a second derivative, and that will give us the same limit as the true value. What if the second derivative is also indeterminate? Well, carry on and find the third derivative and the fourth derivative. A little bit of background on Guillaume de L'Hopital. Apparently, in 1696, he published a book with this rule in, and so it's named after him. Though apparently, it's believed that the person who first came up with it was Johann Bernoulli, a Swiss mathematician. Let's have a look at an example. Here's our first one. So we're finding the limit of this function as x tends to 1. So we sub in our values, and if values, so both numerator and denominator, are tending to 0, so we've got the indeterminate form. So we need to use L'Hopital's rule. And so we find the derivatives of numerator and denominator, sub in the same value, x equals 1, and we've got our limit. The limit of ln x over x squared minus 1 as x tends to 1 is indeed a half. Let's look at one more. So this time we're looking at what happens to our function as x tends to 0. Well, we substitute in and we find the numerator and the denominator both tend towards 0. It's the indeterminate form. So we need to use L'Hopital's rule and find the derivative of both functions. Now sub in our value of 0, still indeterminate. So now we turn to our second derivative. Sub in our value of 0, and we've got the limit. The limit is 2. To finish off, when we are struggling to find our limits, because it's the indeterminate form, we use calculus to find the derivatives of the functions, and we go to L'Hopital to use his rule.